Good morning, everybody. Welcome to the High Energy Density Science Center seminar series. Today with us we have Dr. Cameron Geddes, who is a senior scientist and deputy director of the Bella Center at Lawrence Berkeley National Laboratory. He joined Berkeley Lab in 2000, investigating the use of laser-driven plasma waves to build compact next-generation particle accelerators and photon sources. His work includes compact sources of near monochromatic MeV photons for nuclear applications, as well as extending the future reach of high energy physics and sources of radiation in the X-ray to terahertz band. His work in the center has established several key laser plasma accelerator properties, including high intensity laser guiding for increased energies, narrow energy spread beams, and plasma density gradient injection for control. His current project has demonstrated reliable low energy spread injectors using colliding lasers, as well as 250 MeV energies using 10 terawatt lasers of transportable size. He's also established that such accelerators produce low emittance using Betatron radiation and developed detector techniques for precise spectroscopy. He received his PhD in 2005 at the University of California, Berkeley, supported by the Hertz Fellowship, and he received both the Hertz and APS Rosenbuch dissertation prizes for the first laser plasma accelerator producing monoenergetic beams, which was also featured on the cover as a top 10 discovery by Nature. And previously he received his bachelor's from Swarthmore in 1997 and the APS Apgar and Swarthmore Elmore prizes for thesis work on spheromac equilibria. He also worked in ICF plasmas at Livermore, wave mixing at Polymath, and small aspect tokamaks at Princeton and the University of Wisconsin. More recently, he has been awarded the fellowship in the American Physical Society, and in 2010, the John Dawson Award for Excellence in Plasma Physics Research. I'd like to tell everybody that today's seminar is recorded, so if you're uncomfortable with that, please walk off. And also, it's an unclassified meeting, and we have external people logged in. Please keep that in mind. If you have any questions, please enter it in the chat field, and I will read them at the end. Otherwise, I'd like to extend a warm welcome to Dr. Geddes, and please take it away.
Thank you, Paul. Thank you for having me here and for that kind introduction. And as Paul mentioned, I got my start in doing laser plasma work here at Livermore, including with some folks that I see online. I see Bob Kirkwood online and several others. That was a fantastic experience. And as I'll say today, we continue to have very strong collaborations with Livermore. And I hope that this seminar will bring up some additional areas for potential discussion. And I'll look forward to that as we finish. So as Paul said, I'm going to talk broadly about the plasma acceleration and high energy density science work that we do at the Bella Center at Berkeley Lab. So this is a summary of the Berkeley Lab current personnel in the Bella Center, and I see several of our alumni here as well. It's great to see you also, and I'm glad to see you at Livermore. And so I'm serving under Eric Esray, who's our director, as the deputy for experiments and primarily responsible for the experimental programs. And so this is an overview of our experimental facilities, and we have a suite of lasers that are driving both plasma acceleration and high energy density science capabilities. And our flagship for high energy physics work is the Bella petawatt laser, which is a 1 Hertz petawatt 30 femtosecond titanium sapphire system. And we have two complementary systems that are at the 100 terawatt level. Those are dedicated to photon source development and to high energy density science. One up here in the upper right corner is primarily dedicated to the generation of MeV penetrating photons using Thomson scattering. And another down here in the right corner is dedicated to research on compact free electron lasers. And we also have a compact kilohertz millijoule system that sits in this area. And in addition to the high energy physics oriented work, this system in the upper right is a multi-beam system that supports diverse high energy density science work, including under LaserNet US. And we've also fielded several high energy density science experiments on the first beamline of the Bella petawatt laser. And we're right now in the process of installing two new capabilities on that petawatt laser. There is a so-called second beamline, which will split half of the energy of that petawatt laser and deliver it to the same interaction chamber. This is what we call the first interaction chamber of the Bella Padua here. Deliver that to that same interaction chamber in an orthogonal geometry to the main beam here. So that's designed to allow, as I'll talk about later, for staged plasma acceleration experiments, but it also has a lot of interest for versatile multi-beam high energy density science experiments. And at the same time, we're installing an additional target chamber over at the left here that's funded by Fusion Energy Sciences and will be dedicated to high intensity, high energy density science experiments such as ion acceleration. And that will bring the beam through this first target chamber, allowing us to do things like double plasma mirrors for contrast cleaning. So that's our current suite of things, and I'll talk later about those projects, the IP2 and second beamline projects, and I'll also talk about our future initiatives, which are aimed primarily not at increasing laser energies, but at increasing laser precision and repetition rate, and in particular pushing high energy ultrafast lasers like these to the kilohertz rate. And we also have other initiatives to push forward further applications of high energy density science with an expanded area here for a ion acceleration beamline. So we do this in order to use ultra-intense lasers to advance the fundamental frontiers of physics and to develop applications across industry and society. So that includes particle colliders for high-energy physics and for nuclear science. So for example, to generate TeV beams of electrons and of positrons and to collide them to extend the energy frontier and to access exotic nuclear states. And at the same time, we're developing novel sources of compact coherent X-rays. This is to bring the capabilities of machines like the LCLS or the ALS to industrial or clinical settings where compact FELs can enable us to broadly access ultra-fast science. We're developing sources based on acceleration of electrons and scattering of them against a counter-propagating laser. There's work on this. I saw Rourke Marsh on the call, in particular, using conventional particle accelerators. Using plasma accelerators, of course, our focus is on making those systems much smaller such that we can generate penetrating beams of MEV monoenergetic X-rays to enhance things like interrogation for nuclear security and industrial and medical imaging. And then all of these sources also apply to high energy density science and to oncology in the medical context to provide precision probes using X-rays, ions, and other media of high energy density science. So today I'll talk about each of those areas. I'll start by talking about plasma accelerators. Those are really the core of our program and their application to high energy physics. And then I'll talk about advanced sources of ions and photons and their applications in high energy density science. And then I'll close by talking about our view forward, which is to push these things to a kilohertz precision frontier to further advance the precision and performance of these sources and make them useful for industry and for basic science. So the Bella Center is really primarily focused on executing the U.S. Advanced Accelerator Development Strategy. And this is a strategy with high energy physics, part of the Department of Energy. That's a strategy for taking plasma-based accelerators and using them to develop new types of particle colliders. And this is a very lofty goal, and I'll talk about the steps that have to go into it. So right now, we're deeply engaged in developing 10GeV accelerator modules. And as I mentioned, we're installing a capability to enable us to do staging. That, together with our phase space shaping and injection control, all of the techniques that go into high quality beams, are our core program. And we're developing the capability in staging, capabilities in positron acceleration and in final focus. And we're also working, as I mentioned, on first applications, because a collider will require not just these modules and not just operating at the repetition rates that we can do with our current lasers, but it will require staging of hundreds of these modules together and their operation at tens of kilohertz and at beam parameters that are an order of magnitude beyond what we can do now. So for that reason, first applications such as radiation sources are very important, not only to provide essentially a basis for early applications that can support the technology, but also because they have important synergy, that is, components in common with this mission. For example, staging can be used to deaccelerate particles after the production of photons to limit undesired radiation in a photon source. And so that's a synergy that's important that we develop. And then, as I mentioned, a major focus of ours is future lasers, because while our lasers now run at 1 hertz, which is considered a high repetition rate in the ultra-intense laser field. For the applications, including a collider and also light sources, we'll need to go to kilohertz repetition rates. And a prototype system would be at the kilohertz level, and then collider scale systems would be at the tens of kilohertz scale. And so we need to push lasers from where they are right now. Bella is a 40-watt class laser system to the kilowatts, then tens of kilowatts, then hundreds of kilowatts in order to support a future collider design. So we're doing that based on this laser plasma acceleration technology. I think most of you are probably familiar with it, but for those who aren't, I just want to remark on a few differences that it has from many other areas of plasma physics and high energy density science. Whether it's in magnetic fusion or in inertial fusion or high energy density science experiments, typically plasma experiments are done in cases where the plasma process of interest occurs over timescales that are long compared to the fundamental oscillation periods of the plasma. That is, we're confining the plasma or we're allowing it to expand over many of its own intrinsic oscillation periods. And as a result, much of the physics that we're talking about is physics of confinement, physics of instabilities, physics of shocks, and things like that. So that's not the primary physics of plasma accelerators, because what we're doing is we're using a very intense, very short laser pulse. This is in red showing a laser pulse with its individual wavefronts resolved from simulation, propagating from left to right. And the blue color scale shows the density of the plasma electrons. And what you can see is that the laser pulse radiation pressure snowplows the electrons ahead of the laser pulse and diverts them out to the sides, creating high densities of plasma ahead of the laser pulse and to the sides, and a low density following the laser pulse. The ions are too heavy to move on these timescales, and so they remain stationary, and their restoring force pulls the electrons back, creating an oscillation. That is, we have a laser pulse, then we have a low electron density following it, then a high density, then a low density created by that restoring force. And our particle bunch is going to sit in this first oscillation period behind the laser pulse, or in some cases in the second oscillation period. So we're doing resonant excitation. Our laser pulse is shorter than the shortest oscillation period in the plasma, the electron-positron oscillation. Our structure length will be determined essentially by 2 pi c over the plasma frequency. And so this is a resonantly excited structure that's very fast. And the nice thing about that is that that's enabled accurate scaling laws for charge, energy, and laser requirements. So the simplest is just this plasma frequency that I already covered. And that implies that for typical parameters, we'll have about 100 micron structure. You can also derive the gradient that corresponds to full excitation. That is, you're fully perturbing the plasma. And it's at the order of 10 gigavolts per meter, which is many orders of magnitude beyond conventional accelerators and is really the fundamental interest in this technology. You can also derive the energy that you can achieve before this laser pulse both depletes its energy into the plasma and before the electrons, which can actually travel more quickly than the group velocity of the laser in the plasma, outrun it. And that could be 10 gigavolts per stage in tens of centimeters. And so these scalings actually have turned out to be rather verified by experiments. And this is an example of the energy scalings and showing the energy achieved versus the plasma density across multiple laboratories and many years of experiments. There is an exception down here in Austin in 2013. They used a longer laser pulse that wasn't quite resonant, and so that deviated a bit from the scaling, and there are others that deviate as well. But overall, these reliable scalings have allowed us to design accelerator systems and to anticipate the performance from a given laser with accuracy that, at least in the plasma field, is relatively high. And so that's been one of the things that's supported relatively rapid progress in this field, and the ability to push these systems towards ever higher precision and ever higher beam quality. So these are examples of results from the Bella Center. In 2004, we achieved our first monoenergetic beams at 80 MeV. And ever since then, we've been building successively larger systems and operating them at lower plasma density in order to push the beam energy up. And that's really the key. In order to get higher beam energy, you have to operate at lower plasma density, because that allows the laser pulse to propagate further before it depletes its energy and before the particles outrun it. And correspondingly, because at lower density, your structure period expands according to that 1 over omega p scaling, you need correspondingly a larger diameter, longer laser pulse, therefore with more energy. So 2004, 10 terawatts, 100 MeV. 2006, 40 terawatts, a GeV. In 2014, we brought the Bella petawatt laser online, and as I'll talk about, we almost immediately got 4 GeV, but we really couldn't use the whole laser, and I'll talk about the reason why that was the case. And most recently, we're now approaching the potential of that laser at 8 GeV. And at the same time, we've done experiments preliminarily showing that we could combine 2 stages. So far, just at the couple hundred MeV level, showing that we could either add or subtract energy from a beam in a second plasma stage. And I'll talk about our future plans in that area as well. So our tool for pushing forward the energy frontier of plasma accelerators right now is our Bella petawatt system, which enables us to do experiments at 1 hertz with 40 joules on target and 1% level fluctuation. That's, of course, much more than energy is important here. We're propagating a beam through a plasma over tens of centimeters in a guiding structure, as I'll talk about in a moment. And so that requires a great deal of precision, and that's a big part of our focus on the laser system. So our laser is one of the lower pointing fluctuation systems that we're aware of at about 1 microradian in pointing. But even that is a challenge, because if you think about aiming a beam at a target, we're going to focus to about 50 micron focal spot, and our focal length is such that even this 1 microradian corresponds to a significant fraction of the focal spot size. And so that's already something that we need to control, and I'll come back to that at the end of the talk, how we're working to do that. This is a pulse that has about 75% of its energy in the main structure with about a 6% peak fluence variation. So as you can see, you put 1% level fluctuation in energy, that sounds pretty good. But as you start building up the different factors, this variation does start to increase. You have a variation in focal form. Then you also have compression to about 33 femtoseconds. But there's also, of course, a variation in the temporal pulse form that contributes. And so that both of those roll into the peak intensity, which has about an 8% fluctuation. And I'll talk a little bit more in a moment about the contrast, which is at about the 10 to the 9 level. So measurement and characterization of the laser is a large fraction of what we do in order to deliver it to target, both for plasma acceleration and high energy density science experiments. The laser is actively controlled, although at relatively low repetition rate. I'll talk at the end of the talk about high frequency pointing correction. But we measure, for example, the pulse front tilt resulting from misalignment of the gratings that compress the laser and optimize that in order to control the propagation of the laser. We use deformable mirrors to improve the focal form of the laser. And we use cross-polarized wave filters and other techniques to suppress undesired pre-pulses. And this is an example of one of our contrast scans showing the elimination of one of the key features that was limiting us in the past, and pre-pulse contrast about 10 to 9 in this case. So why is all of this important? This is an illustration of the physics that went into that 4 GeV result and that limited it. So if we look at the focal spot of our laser in vacuum, it looks reasonably good. It has a strong central feature and a little bit of halo around it. So you could fit a Gaussian into that and think that a lot of the energy was in a Gaussian, but that's really not actually true, because what's happening here is we have what's really a quasi-flat top mode. So this is showing the vacuum near field of the laser. This is obviously a diagnostic cutout. We don't have a hole in the mode. But we do have a quasi-flat top beam that has also high frequency spatial structure. And so all of those things then come to play when we need to propagate the beam over a long distance in the plasma. And for that 4 GeV experiment, that distance was about 6 to 8 centimeters. And so what you can see, these are simulations showing how a Gaussian beam would propagate in a given channel. And then looking at this more realistic profile, in this case, just the radially symmetrized part, not all of this high frequency content. And you can see that that top hat beam does not propagate in the same way. And in particular, this is a contour of the outer edge of the beam. And you can see that there's much more energy at large radius that can damage the guide. And so what that then means is that in order to guide this top hat beam, you have to actually go to a higher plasma density than you otherwise would. And that influences the parameters you can access. And in fact, it was the limit in those 4GeV experiments. This was our capillary plasma channel. The plasma form here is shown that it's a particular channel that we used, and it wasn't able to guide the top hat beam at the low densities that we required. And so the result was that if we looked at the intensity evolution of the laser across that structure, it was evolving strongly and in a complicated way that turned out to really influence injection and to limit the energies to which we could go in those experiments. So we've focused in the past years on measuring the laser pulse. And you see that here, a laser pulse propagating, and you can see its wave fronts resolved in time and in space. And you might think that this is a simulation, but in fact, this is a measurement. And we're actually very excited about this. This is a new technique that's being developed and was published recently by our collaborators at CEA, along with our staff. Kei Nakamura led this measurement at LBL. Using interferometric techniques, we're actually now able to measure in space and in time the phase and the wave fronts of a laser pulse. And so this now gives us the tools to optimize that laser pulse. And an important point that I'll return to at the end of the talk is that in many cases, we're coming up against the fluctuation limit in these optimizations. And so we need to have active stabilization systems that go to higher bandwidth. So while this system is, I would say, state of the art, it's still a system that needs to be improved to support increased performance in the future. So let me talk a little bit further about how we do that and how we apply that in experiments. So as I mentioned, our past experiments demonstrated 4GeV using a capillary waveguide. So for those who are unfamiliar, this is what that means. We have our Bella drive laser up here at the right, which comes in and is focused by an off-axis paraboloid, then delivered off of a final steering mirror into what we call a capillary discharge waveguide. So what you see here is a picture of that guide, and most of what you see is the plastic structure around it. This very fine filament through the middle is a hole that has been laser machined through the sapphire block, and the laser is actually propagating through that hole. And before the laser pulse arrives, we run an electrical discharge down that plasma column, the hydrogen column here. The discharge ionizes the hydrogen and forms a plasma, and it forms a structure that looks like this at the bottom right, with a minimum density on axis and a rising density off axis. And the reason for that is that we're heating the plasma by ohmic heating, and we're then cooling it at the wall here. So that means the temperature is cold here, warm here, and that drives a difference in densities. But as you saw from the simulations I showed you a couple of slides ago, while that was sufficient to allow us to guide at a density of 710 to the 17, it was not sufficient to allow us to guide at lower densities. And that's what limited us to the 4G in that 2014 result. And so it was realized then that we could do better by additionally shaping this guide. And so we added an additional beam, which we call the heater pulse. This is a 10 nanosecond duration jewel class beam. It's actually what would commonly be used as a pump laser for many of our systems. That's coupled in through the back of the steering mirror for the main beam into the capillary. And so it's guided by the capillary structure, and it heats only the center of the guide. And so that results in evolution that looks like this. As we put the guiding heater laser down the guide, it heats the center of the guide, and then hydrodynamic motion causes the center of the guide to deepen. So you can see these two distinct structures, the gradual slope that's created by the capillary discharge and the steeper slope that's created by laser heating. And so that allowed us to dramatically deepen the guiding profile at a given density. And correspondingly, that allowed us to lower the density at which we could guide the laser pulse, and hence to go up along that ladder of energy. So in 2018, via optimization of this process, and in particular, Tony Gonzalez led this study, realization that the head of the laser pulse, the heater laser pulse, starts to form this guide, but you can see that this time scale is pretty short. So the tail of the heater laser pulse is actually seeing part of that guiding structure, and that allowed us to improve this effect and allowed us to access densities at which we could, using about 0.85 petawatt, access energies of about 8 GeV in this laser heated capillary. So that's now approaching the energies that were predicted for the Bella petawatt system, which were 10 GeV. We're still not quite there. Part of that is because of our need to restore the laser to its full operational performance. The laser is rated to perform at a bit over a petawatt due to degradation over time of the optics in the pump lasers. It's not quite at that level, and we're in the process of refurbishing it. And it also requires us to further control the shaping of the guide and to better control injection into the structure. These experiments are still essentially self-injected. That is, we're driving the wake up to a very high amplitude and allowing it to inject particles from the background plasma instead of using an independent control method. So in preparation for those experiments, right now we're in a shutdown period for installation of those new capabilities. So Marlena Turner has been leading characterizations of the capillary waveguides. One of the questions that we had was, are the capillary guides contributing to the fluctuation in the experiments? And so she did very precise measurements using a fiber input to have a very stable input pulse to the guide and using a camera to measure the output for a variety of guide lengths ranging from 9 centimeter, this is about our 4 GeV result, all the way up to 40 centimeter that would be applicable to a 10 GeV stage. And the findings are that the axis is extraordinarily stable to less than a micron and does not explain variation in LPA. So that's great because it tells us what we need to focus on. We need to focus on controlling the pointing of the laser into this stage. And again, I'll return to that late in the talk. So our focus this year is on installation of the new capabilities. And as I mentioned earlier, the first of those is this so-called second beamline that will take part of the petawatt laser and deliver it to the same chamber in order to support either multi-stage plasma acceleration or other experiments. So this experiment has been designed to offer a lot of flexibility. So this shows you the routing of the beam from the output of the laser to the compressor. This will be a new pulse compressor complementing the existing pulse compressor that is over at the right here, to a set of routing chambers. And these chambers look a little bit odd at the start. They're much larger than would be needed. And the reason for that is that they support multiple routing options such that we can change the focused spot size on target, which is one of the most difficult things to do for plasma acceleration, but is really critical to allow us to optimize stage regimes. So we'll use that to access new regimes in plasma acceleration. We'll also use it to couple the first part of the laser to drive a first stage, take the electron beam out of that, through a plasma mirror, use this second beamline capability to deliver a second laser to a second plasma stage. And as I noted, we've done that at the 100 MeV level. This will be the realization of that at the GeV class. And it'll also provide a platform for a lot of other exciting experiments. That second laser could be used instead to form a waveguide or as an injector. And it could be used, for example, to generate an LPA electron beam, then convert that in a high Z target to positrons and capture those in a second LPA. So this is going to offer a lot of exciting physics ahead, not only in the MultiGEV staging, which is its primary goal with high energy physics, but in the longer term future, of course, this is essentially two configurable pulses deliverable to a chamber. Each could be half a petawatt, or the primary line, and possibly the secondary line could be up to a petawatt, allowing variable splitting. That could really enable a lot of interesting multi-beam high energy density science at petawatt scale. So that to return to that primary mission, the beamline's primary mission is multi-GeV staging. And so this is showing you a simulation of a few GeV stage based on half of the Bella petawatt laser. And that'll be based on scaling our past results in controlled injection. So I mentioned that our highest energy experiments are self-injected, but we have an array of other experiments that are dedicated to mechanisms for controlling the plasma accelerator. And one of those is injection control. And so what this shows is an experiment by Tony and collaborators where they use two different gases. So this again is a side image of the capillary showing you the hydrogen gas that primarily fills it. And you can see the glow all along the capillary as well as in these little fill slots that are at the sides. And what they were able to do is to dope just a little bit of helium into the plasma only in one of the slots. And you can see that helium remains very localized. And what that allows them to do is to produce very narrow energy spread beams. And so we'll be implementing that into our multi-GeV stages and using it to support the staging experiments. And the indication is that by doing this in a first stage, and then by adding a second stage, we'll be able to do a multi-GeV staging experiment in the near term. It's notable, however, that we will still be limited by the quality of the injected beam. That is, this beam, you can see it has narrow energy spread, but it does not have narrow divergence. And that's a signature of the fact that we're using this ionization process to do injection, which does not produce low emittance. The result of that is that we'll be able to select as a function of delay either high capture efficiency or energies approaching 10 GeV and 8 GeV combined stage energy. And to go further, to realize 10 GeV staging will require both a low emittance injector and a better matched guide than we can currently do. And so those are other series of experiments and of research that we're focused on in the coming years, both internally and in collaboration with external groups. So one example of that is, I alluded to the fact that we'll now have multiple beams in the chamber and the ability to do experiments using those on particle injection. One of the promising techniques is to drive the wake with one beam. So this is showing a drive laser beam propagating from the lower left to the upper right here, exciting a wake, and then an injection laser pulse follows it that's of higher frequency, and that allows us to inject particles with very low emittance into the plasma structure. So techniques like this for fine control of the injector and fine control of the guide are some of the really key things for the future of this plasma accelerator field going forward, and to push us to 10 GeV and beyond, and also to allow us to address the needs of colliders and other applications for both high efficiency and high beam quality. So with that, I want to make a little bit of a transition and talk about nearer term applications. So far I've been talking about our high energy thrust that is most directed at high energy particle physics. And so I want to take a step back from that now and talk about nearer term applications, including those in high energy density science. So I want to start with ion acceleration. And we have an in-operation capability right now using our existing long focal length capability. It has a large spot incident on a foil. This accesses the so-called target normal sheath acceleration regime, where particles are accelerated by essentially heating an electron population around this foil, and those then pull ions out of the foil. And as I mentioned, we're in the process of installing a new short focal length capability, which will allow us to go from intensities of the 210 to the 19 scale to intensities of the 210 to the 21 scale in a smaller laser spot to do ultra-relativistic plasma science and to hopefully access some of these advanced acceleration mechanisms for ions, where, for example, at sufficient intensities, the radiation pressure of this laser could push this entire foil along, accomplishing radiation pressure, or what's sometimes known as light sail acceleration. And I also want to note in doing this that this is a rich area of Livermore collaboration. Many people listed at the bottom, including Tammy Ma, Scott Wilkes, Derek Mariscal, Graham Scott, Elizabeth Grace, Kelly Swanson, and Raspberry Simpson, who are both doing experiments with us under our user program, and where we're starting collaborations on other topics as well, and we really look forward to that. So some past results from the Bella Center on that sort of large spot size TNSA regime. We've used the high repetition rate of the laser to enable us to do really highly statistically relevant experiments. And I think this is one of the distinguishing capabilities that we have. So this shows a scan of the laser pulse compression. This is an article that was recently published by Sven Steinke, showing that as you change the laser pulse compression, as expected, at long pulses, you get low energies, and that increases. But there's actually an optimum that's slightly away from best compression. And that was explained essentially by a sweeping effect in the laser spot. And so that's an example of the detailed physics that you can do with high repetition rate and that we think will be exciting in years coming forward. So we then take that laser-produced ion beam and we start to think about how to use it. So our plasma capillaries can be used not only to guide laser pulses, but also as high-field plasma lenses. So I've got a tube here of plasma that has an axial current along it. That axial current means an azimuthal magnetic field. So that azimuthal magnetic field is symmetrically focusing, and it can focus either ions or electrons, depending on the direction of the current, of course. And so this shows the discharge focusing of a proton beam onto a secondary target and onto a spectrometer. We've then used that setup to do experiments on radiobiology, and there's an article that will be coming out soon showing how photons produced by laser plasma accelerators can access possibly advanced therapy modalities like flash, where you deliver dose very quickly, and that can affect the radiobiological effectiveness of the therapy. And of course, you can have other types of samples. These are examples of targets that Thomas Schenkel is leading for essentially ion implantation and creation of color centers relevant to quantum computing. And so I think this is a platform that has a lot of interesting high energy density science to be done on it, and a lot of collaboration potential with Livermore. At the same time, we are installing that new high intensity laser beamline. As I mentioned, the beam comes through the primary target chamber here. It's brought out, collimated, brought into the new chamber, and then focused for the highest laser intensities at 10 to the 21 watt per square centimeter. And this primary chamber can then be used to house a double plasma mirror for contrast enhancement to achieve very high contrast, which is important at these intensities. I then want to talk a little bit about other types of sources, photon sources specifically. And we have a variety of photon source experiments that we're pushing forward, many of which I think have relevance to high energy density science experiments. So the first is precision MEV monoenergetic beams. And this again is the approach where you generate an electron beam and scatter a laser from it. And the plasma accelerator offers you compactness because you need a several hundred MeV electron beam to do this. And so this could offer precision characterization for applications ranging from the identification of treaty objects to industrial non-destructive evaluation to the scanning of cargo. And so you can imagine a scenario where instead of putting a wash of broadband and broad angle photons across something like a truck, you have a beam that you can target and that you can sweep, and where you could actually adapt dose to put the most dose where it's needed, and where you could adapt both energy and flux in order to have high specificity identification. And this photon source project also involves some collaborations with Livermore on simulations, in particular Dave Grody and Alex Friedman. And it's accomplished using a multi-beam laser system that delivers a primary beam to target to drive the plasma accelerator, as well as a secondary beam to accomplish the Thomson scattering. And that also provides a flexible platform for multi-beam high energy density science experiments, including some upcoming experiments with Derek and Tammy and Raspberry and many others coming up on this system under LaserNet. We have a second 100 terawatt system that's devoted to the development of compact free electron lasers to make accessible coherent ultra-fast science. So I'll talk a little bit about each of those systems. So this is the diagram of the monoenergetic MEV system. It's a 100 terawatt laser facility with a laser bay and a interaction chamber here that offers us the ability to configure multiple beams on target and then a separate photon source experimental area. And the exciting thing about this source, in particular for high energy density science, is that it enables precision measurements, by which we mean sensitive detection of materials below the micron scale in resolution and the picosecond scale in temporal resolution. And this again is that picture of the overlap of the beams, the drive beam for the laser and the scattering beam, showing how that's accomplished with our cameras and showing the scintillator detecting the photons. And at right, you can see detection of a beam of about 210 to the 7 photons produced, and that is compatible with all of the electron beam properties that went into it. So we have essentially a checksum. We can calculate the beam that we would expect from the electrons, and then we can measure the beam using the scintillator, and those are compatible. And it's enabled by many hours of stable plasma accelerator performance. And these techniques have the ability to reduce dose and increase specificity in X-ray and CT techniques by 1 to 2 orders of magnitude, and also to support application in LaserNet US experiments for users. So let me talk a little bit more about those advantages. And this, again, is something where Livermore collaboration has been key, including simulations by Brienne Descales, who showed that these types of monoenergetic sources dramatically increase the contrast that you can have between materials. So this is an object where multiple materials are sandwiched together to make something that's very challenging to detect, the kind of thing that someone might do if they were trying to shield a nuclear object from detection. And you can see that a conventional Bremsstrahlung photon source with broad energy spread gets very little contrast even on this very strong transition essentially between plastic and lead, and essentially none between the high Z shielding and the nuclear material. Whereas an appropriately tuned monoenergetic source shown in red can get significant contrast enhancement. You get about a 10-fold increase in contrast. At the same time, you mitigate scattering because the beam is very narrow divergent. So as the beam goes through a thick object, for example, a chunk of steel here, it scatters, but you can essentially separate that at long distance. The small emission spot of the photons also allows you very high resolution in radiography. And so this was the subject of a multi-lab study, including folks at Livermore and at Berkeley, to show that these could improve performance in terms of dose and also in terms of material specificity tenfold. And we have ongoing collaborations and discussions with others at Livermore, including Harry, Steve Glenn, and Joseph Bendehan. And we really look forward to probing some of these applications and also to doing some high energy density science experiments. The second 100 terawatt system is developing a plasma accelerator based free electron laser, where we take that plasma accelerator beam, refocus it. Crucially, our beams are very bright, but their brightness is in the wrong dimension. They have broader energy spread than an FEL wants and shorter pulse length. And so we can essentially compensate for that in a chicane by stretching the beam out, decreasing its slice energy spread and current at the cost of increased duration. But that actually works for the FEL. We then refocus into the undulator, and this system is just beginning to operate. It now has stable electron beams, and the LPA decompression is operating, and the undulator is installed. And over the coming year, we hope to demonstrate first gain around 3 EV with a future scaling path to tens of EV. And eventually, we hope to a compact KEV FEL that, again, could offer a lot of capabilities for high energy density science when partnered with a large driver. So that then brings me to my last point on these sort of types of sources, which is that we are open for collaboration and user access under LaserNet US, which is a network that provides user access for users in high energy density science, in light sources, in measurements using these sources, and also for high energy physics. We definitely are interested in collaborative projects. As I mentioned, we already have several underway, which we're excited to push forward, and we'll welcome discussion with all of you. I want to highlight briefly 2 of those that are relevant in this area. One is a collaboration both with Carolyn Carance's group at Michigan, and also Philly C and others here are involved, as well as Raspberry and Elizabeth. And here we use a plasma accelerator, we accelerate an electron beam, and we just let the electrons oscillate in the strong transverse fields of the accelerator itself. And that produces broadband KEV X-rays that we're using to sense the shock driven in a water jet by a secondary shock driving laser. So this provides us the possibility of a high energy density science platform with micron resolution and with femtosecond resolution at 1 to 5 hertz repetition rate, so that we can really do precision hydrodynamics. I think that a lot of high energy density science experiments we do using big drivers, we get single data points. And so here we have the opportunity to do experiments at lower energy. So we have a lot of scaling to do, but with great power in both resolution and in the ability to take many, many frames in order to understand the detailed physics of the phenomena. So at the right, you see a demonstration of the micron resolution of the imaging system. And I'm excited to say that in the last days of the campaign, we did get water shock images in that campaign, demonstrating that this platform can work and can sense shocks in water jets. And so that precision imaging is ongoing. And as I'll touch on at the end of the talk, this is right now at 1 hertz, but these types of lasers, these energies of lasers have a future at the kilohertz repetition rate. So you can literally imagine doing tens of thousands, hundreds of thousands of shots of this type of experiment to build up a tremendous power in both temporal resolution, spatial resolution, and eventually things like tomography. Another LaserNet US experiment that's been very exciting has been a collaboration with Ohio State University, which showed that we could field a double plasma mirror based on the liquid crystal targets that Ohio State has developed. So most plasma mirrors are based either on solid substrates or in a few cases on either translatable tapes or other things. All of those things have both debris problems and essentially shot number problems. So if Bella operates at 1 hertz, we will take 10,000, 20,000 or more shots in a shift. So we need something that's renewable, that's low debris, and that's high in quality. And so Ohio State has demonstrated that they can use liquid crystal films as mirrors. And in this experiment, we fielded 2 of those plasma mirrors and used them as a plasma mirror configuration. And that required not just implementation of these 2 spinning rotators. Each of these has wipers that put little films into each of these holes so that a film is ready when the laser comes along to reflect and then reflect again. But each film is formed at a very slightly different angle because of surface tension effects and imperfections in the apertures. And so we had to implement active beam correction with Ohio State. And we demonstrated that not only does this work, not only does it reduce pre-pulses, but we also demonstrated that these thin pulses are suitable for transmission of an electron beam and hence for use in plasma accelerator staging with reduced emittance growth due to scattering in the film. And this is that experiment here, same type of setup, but here instead of having 2 plasma mirrors, we just have a single gas cell forming the plasma accelerator and a single plasma mirror that diverts the laser pulse. And then we measure that electron beam and show that we can reduce the scattering and reduce the emittance degradation. So these all developed techniques that I think have the possibility for a very exciting high energy density science platform, where right now we take relatively few images with resolution that has limits due to a variety of factors. And so I think the sources that we're developing have a lot of potential to produce in the near term, the types of KEV, micron resolution, broadband sources that we can do with Betatron. We're also now producing MEV monoenergetic sources with micron resolution that could be useful to penetrate dense imploded cores that aren't currently accessible at that type of resolution. We can produce ions with the same lasers for field imaging, and eventually we can produce coherent KEV sources to bring the kind of power that's now only available at machines like the LCLS to other facilities. So this has the potential for advanced imaging to enable precision high energy density science. And here I definitely want to acknowledge Felicie's pioneering work in many of these sources and their applications to high energy density science. And so I'll just put this up there. I'm not going to go through it in detail, but I think it would be interesting to pursue with you all, what are the constraints, what are the needs for diagnostics, and how do we meet them with these advanced sources? And so with that, I want to close with just a few minutes on where we see and our thrust in the frontier of high energy density science and plasma acceleration, which is to push forward the kilohertz and precision aspects. So there are many needs to push forward the science of high energy density plasmas and of plasma accelerators. But in particular, we're focused on the fact that while the potential of plasma accelerators has been shown, an order of magnitude performance increase is needed for application, and that requires precision. And at the same time, I've talked a little bit about some of the potentials for precision science when you could do thousands or tens of thousands of shots in order to really do precision science and precision scaling. So one could do some of this, in particular, increase plasma accelerator efficiency just by increasing laser energy. But that's not an efficient approach. In particular, for a collider, we have to be very focused on that. So instead, what we need to do, as I've talked about throughout this talk, is precision shaping of the laser. And here we have a challenge with our current systems because we have ground motion and air motion that essentially mean that if we correct on one shot, it's not right on the next shot. And so we've measured our systems and shown that those motions fall off around 100 to 200 hertz. And so we could correct those things at kilohertz and enable essentially a new frontier in precision. So right now, kilohertz lasers are limited to relatively low energies, and we have a kilohertz millijoule test bed that we're using to develop some of these things, such as active laser pointing stabilization with a 10-fold improvement demonstrated, and active laser mode correction in progress. And we need to do that also on higher energy lasers. And so you could ask, what can we do now? Well, the thing we can do now is we can take a laser that has a high repetition rate front end, a kilohertz front end, amplify that up, but preserve the kilohertz low energy train as we do so. And if we do that, we can use that kilohertz low energy train to do correction. And what this shows, this is a paper recently submitted by Fumika Isono, that we can correct a significant fraction of the Poynting variation by doing that. But this, of course, doesn't correct everything. It doesn't, in particular, correct effects due to pumping and to different beam sizes between those two pulses. So we're developing designs for high energy kilohertz lasers. And I'll go through this very quickly and I'll welcome questions on it. But we have a design that's been developed for a titanium sapphire design using diode pump lasers and cryogenic heat extraction together with new dielectric gratings that are from Livermore. And so that design is ready to build. But at the same time, we want to push forward laser technology to be able to build systems at high efficiency for future needs. So at Berkeley, we have a project in collaboration with University of Michigan and Livermore, Aleli Kiani in particular, developing an architecture for combining multiple fibers. That is, that you would generate a series of pulses, split them, amplify in many channels, and then recombine them to make a single high energy pulse. And so this is a high efficiency path that could scale to collider needs. And I won't go too much into the details of that, but I want to highlight that it's one of two major approaches to high efficiency lasers. So one is this idea that you would combine many fibers. The other is that you would use a new media, and that's something that's being led by Livermore, in particular Tom Spinka and many colleagues here. And both of these are under development and I think have very promising futures. And I think we want to push them forward from where they are now, being demonstrations of technologies, to really the ability to build first some relatively modest systems at the hundreds of millijoules, and then to have a future path to highly efficient tens of kilohertz joule class systems to be able to drive the next generation of plasma accelerators and of high energy density science. So that's a major thrust for Berkeley Lab right now, is to build such a facility. It's part of many planning activities alongside other exciting new laser facilities like the MEC upgrade at SLAC and a potential multi-petawatt system at Rochester and many others. And this system would serve that need to have a kilohertz and eventually multi-kilohertz capability to push forward plasma acceleration and precision high energy density science. So with that, I'd like to close and welcome your questions and discussion. Thank you.
Yes, please unmute yourself to give Cameron a nice big applause. And also in the meantime, please enter your questions in the chat field. Thank you. Yes, well, we're waiting for people to type. I'll ask the question of my own. So I thought it was really cool how you were able to image the wavefront of laser passing medium. Could you speak a little bit more about what went into actually developing that technology, and also what kinds of cool things do you envision doing with it? I imagine there's all sorts of testing of all sorts of diagnostics you can develop, and also testing of various models, and basically it lets you see very detailed information that we otherwise haven't had access to.
Yeah, absolutely. So the fundamental technique I want to acknowledge was initiated at CEA, and it is a technique where you take the laser pulse, you split it, aperture one part of the laser pulse to make essentially a clean copy. So in this sense, this is similar to doing something in the temporal domain. For example, in a TOAC, you third order autocorrelator, you would double part of the beam to make a presumed clean reference copy, and then you would combine that back with the original beam, right? So this is similar in the spatial domain in a sense, that you split the beam and then you essentially self-reference it in an interferometric configuration, and then you're scanning delay in order to reconstruct that image. And so this is a multi-shot technique at this time, which is why it took time and why it took repetition rate. But nonetheless, as you say, it's very exciting. So one of the key questions that we had is that all of our other diagnostics are temporally resolved, or temporally integrated. So you get a spot of your laser pulse, but you don't really know, is that projected spot, is that actually uniform along the length of the laser pulse temporally? Or is, for example, the front of the laser pulse focusing differently from the back of the laser pulse? And in our case, actually, the indication was that that was not a big factor. And so that was a big relief to us. But still, it shows a level of detail, as you say, that is not accessible from other diagnostics. And so when we input our laser pulse, for example, into a simulation, we're almost always inputting a strong approximation and a strong idealization of that laser pulse. And so these types of measurements allow us to better correspond what we simulate to what we to essentially what we have in the experiment. And that was actually the reason why I followed it with that slide about guiding, because these types of structures in the laser pulse really influence how the laser propagates in the target. And that's some of the key physics that we have to control. So it informs us on what controls we need in the laser pulse and how we need to tune it, right? And so that's part of the thrust that I returned to at the end of the talk. Some of that we can do at low repetition rate. Some of it requires us to implement pilot beams to have better control. And then, to really control it properly will require higher repetition rate lasers. And there's a sequence of things that we can do both on current facilities and using new facilities.
Thank you very much. So there's a question from Scott Wilkes. This is a great talk, and just wondering whether the fact that one of the future lasers operate at 2 microns help or hurt you?
Yeah, it's a really interesting question. I think it varies by application, obviously. So it turns out that for plasma acceleration specifically, there are different constraints on a collider than on a photon source. So for a photon source, you would like a particular electron energy out of a single stage, typically, because you don't want to do multiple stages and suffer that complexity. And in that case, essentially going to longer wavelengths, if you want to keep the same electron energy, you need to drop down the plasma density. And there's an easy way to understand that, right? You want to keep the ratio of the plasma frequency to the laser frequency such that your laser propagates and excites the wake over a sufficient distance to achieve the same energy, right? So what does that mean? So at 2 micron relative to 1 micron, you go to lower plasma density. If you keep the rest of the scalings constant, what that implies is that you would need a higher energy laser by a factor of 2. But in trade, you could use a longer pulse duration and you would get more charge out of the accelerator. So it doesn't change the efficiency of the accelerator. It just changes the amount of essentially charge that you would get at a given energy. And for most applications, that's okay. For a collider, on the other hand, one of the key bindings is that when you get to the interaction point of the collider, you have to collide these two beams together, and you want to operate with a charge that is as high as you can, because essentially the number of events you get is the number of particles in this bunch times the number of particles in this bunch times the cross section, right? So it goes as n squared sigma. So that would imply that you want a lot of particles in the bunch. But eventually, as you increase the particle number in the bunches, these bunches will essentially electromagnetically interact and tear each other apart. So a beam-beam interaction. So essentially, a collider will have a specified number of particles in the bunch limited by that interaction. So now we're not specifying the energy of a particular plasma accelerator stage, we're specifying the particle number. So now, instead, what will happen is we'll actually need a larger number of stages at a lower per stage laser energy from the 2 micron. So either of those trade-offs can be managed. Obviously, a larger number of stages is maybe a little challenging, but it's nice to have lower energy lasers. So I think it's that you can accommodate either in either case.
There's a question from Vincent Tang. It says, thank you for your talk. Can you comment on the potential for your source to be used for NRF/SNM detection? What do you think you can achieve with respect to energy spread for your monoenergetic extraction?
Yeah, absolutely. Thank you for that question. So that was part of that application study that I referred to. And essentially for nuclear resonance fluorescence, for those who aren't familiar, nuclear resonance fluorescence lines are very narrow in bandwidth, typically at the level of 10 to the minus 6, in fact. So our sources, in fact, any sources will not access that level of energy spread, but we don't have to. What you need to do is to drive the energy spread of the source down sufficiently that the detectors can then pick up the signal from the background, right? So that's a real challenge with Bremsstrahlung sources. It has been done, but it's very difficult. The simulations that were part of that application study, and in particular, Glenn Warren at PNNL did a large number of these simulations, as well as Brian Queter at Berkeley Lab, indicate that somewhere around 1% energy spread is a regime where the detectors really begin to become much more effective and these measurements begin to become realistic. And at those energy spreads and at kilohertz level repetition rates, you could identify objects of interest, for example, to treaty verification scenarios or to cargo detection scenarios in minutes timescales. So right now, our sources do not access those energy scales. And the reason is, it's actually not the energy spread of the electron beam primarily, it's its divergence. So in Thomson or Compton scattering, you have an electron that comes along and a photon that comes nearly counter-propagating. And you have both an energy spread in the scattered photons that's due to different electron energies, but also photons that are emitted at different angles also have different energies. And so if you have electrons that are at different energies, or sorry, different angles, they will emit different energies along the axis of the beam. So what our simulations indicate is that we have produced in plasma accelerators beams, electron beams, that is, with 1% level energy spread. We need to make those beams more stable. And once we do that, we then need to refocus those beams, probably using that plasma lens technology that I described, to a larger focal spot to reduce its divergence. And if we were to do that, we could then access 1 to 2% level photon energy spreads that would be suitable for NRF. And in fact, simulating ways of doing this has been a big part of Dave Grody's work, and he has a paper on that coming up. So we do see a path for doing that. It will require further source development, which we're definitely excited to do.
So there's a question from Bruce Remington. It says, using some of the techniques that you have developed, does it seem possible for us to reach the electron volt electron acceleration on the NIF arc?
Yeah, so it's an interesting question. So I think actually Philly C may have answered it in the chat a little bit. So yeah, I'll chime into her answer. Yeah, so she's exactly right that the pulse lengths of arc are such that it could only do self-modulated LWFA. So what do we mean by that? We mean that the picture that I gave was a so-called resonant picture where the laser pulse duration is shorter than the plasma period. So for giga-electron volt acceleration, you want a plasma period that's in the tens of micron range. So that implies a tens of femtosecond laser pulse. And of course, arc is much longer than that. So if you put a laser like arc that's long into a plasma that's of an appropriate density for GeV acceleration, it will break itself up into multiple pulses in this self-modulation process that Philly C is referring to. And that will cause a less controlled and usually broader energy spread result. That said, I think that the lasers that are required for GeV acceleration are not actually large. So I think that there are a number of approaches that we could explore together, and I would be interested to do that. And I know Philly C has thought a lot about this. You could consider, could we control self-modulation and/or control injection into a self-modulated wake field? Could we broaden the pulse and increase its bandwidth so it could be compressed to a shorter pulse duration? Or could we pump a laser, an independent laser that's of moderate scale? You only need joules to do this and use that as an alternate approach. So as Philly C says, in order to blow out with arc, you'd need arc to be many petawatts with its current pulse length, or alternatively, you'd need it to be much shorter in pulse duration.
Thanks. And there's a question from Minsheng Wei. Any plan to test the flying focus technique for BTLWFA on Bella?
So not at the moment, but it's certainly something that we would love to do. And we've had some discussions with some folks from LLE. So this is a technique that's been originated at Rochester LLE, which is really interesting. So everything that I've described is focusing of a quasi-Gaussian pulse into a plasma and allowing it to propagate. And so one of the issues that I described is that the pulse propagates at a given velocity in the plasma, and eventually the electrons outrun it. So it was realized by the folks at LLE, including Dustin Frilla and John Pilastra and many others, that you could focus in a different way such that you could create an intensity front that propagates at a controlled velocity. And so I think that's a really interesting approach. It's not one we're funded for right now, but it's one that we would love to identify a way to pursue. And I think that it could be interesting for stages, but my own personal greatest interest in it for Bella would be as an injector, that you could arbitrarily control the propagation velocity and really do interesting things in shaping.
I guess those are all the questions, and let's thank our speaker again. You can unmute yourself, and otherwise, please have a great rest of your Thursday.
Great talk, Cameron. Thank you.
Great. Thank you all very much.